Hey there everyone. We talked about the magnetic field produced by a straight long wire. We also talked about the magnetic field produced by a loop. We found the direction of these magnetic fields. We also found the value of these magnetic fields. One more shape of a current that we need to study in detail and find the magnetic field for is a solenoid. Well, what does a solenoid look like? A solenoid looks like this. It's like a coil, and it's not like a loop. Loop is like this, like concentration of wires that have a certain center in the same plane. But look, the solenoid has kind of it's like a spring. All right, so the solenoid will pass a current, and we don't know how that current, it looks like it's going this way, it's going this way. You're looking at it, you're gonna lose which loop is going in the screen and which one is looping away. So the best way to look at it is just like, I'm gonna assume that we have a block, just to have like some kind of like a visual better understanding, and it looks like this. So there is several loops, and it seems that the loop on the top is going here inside the screen, and from here at the bottom it's coming out from outside, just to give you an idea. And I'm going to assume that the current direction is this direction. So that's my loop, or that's my solenoid that I just made. So the current continues its way coming like this. That's a current I. All right, now we need to find the magnitude and the direction of magnetic field at the center of a solenoid that passes a current I. A good demo for that I just made from my coffee cup, and this is the cylindrical, or kind of like the solenoid that I made. Imagine the coffee cup does not exist. It's just like an object to help us visualize things. So how do you find the magnetic field direction at the center of the solenoid? Look, I made the current direction this way. So you grab on the solenoid such that your four fingers go over where the direction of the current is. Then your thumb here will be actually the direction of the magnetic field. So according to this situation, we have the magnetic field coming from this end and straight through the center of the solenoid, going all the way out. And let's see how this goes here on this one here. So I am going to grab on this with my four fingers here, 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 here. So I'm going to put my four fingers 1, 2, 3, 4 here, and I'm going to grab on it. So my thumb actually goes this way, because that's where my four fingers are. All right, so my thumb goes this way, and this means that the direction of this magnetic field going this way at the center of the solenoid. So it's going this way. Okay, of course it goes like around this way, away from the center a little bit, but we don't care. We just care about the direction of it at the center, and it's just exactly parallel to the center of the solenoid. All right, now we found out the direction of the magnetic field. Let's find out the value of the magnetic field at the center of a solenoid. So magnetic field at the center of a solenoid is equal to mu naught times small n times the current. Now you know what the current is. You know what mu naught is, 4 pi times 10 to minus 7. However, you've never seen n before. You've seen big N, but not small n. And there's a difference. Okay? Small n is the number of loops per unit length. Okay? So number of loops, so small n is equal to the number of loops per unit length. Okay? So what is that? If we have this solenoid here, for this solenoid, it has, this is the length of it, but how many loops does it have? 1, 2, 3, 4, 5, 6, 7, 8. Let's say the length is 20 centimeters. So n, small n, is equal to big N divided by L. N we said is 8. 1, 2, 3, 4, 5, 6, 7, 8. Divided by 20 centimeters, which is 0.2 in meters. And that would be a number, whatever that is. So that's what N here means. Remember, it's not the loop, the number of loops. It's the number of loops per unit length. Okay? And that's it. Thank you very much.